Hi, I'm Fabio, and welcome to a new course about the mathematical foundations of machine learning by martechpost.com. In today's video, we will cover the subject about statistics, the last mile between us and the deep understanding of how machine learning works. So, statistics studies phenomena under a condition of uncertainty, a sort of non-determinism condition. So, making extensive use of probability theory, statistics allows to define and formalize tools for the collection, organization, analysis, interpretation, and presentation of data. And we remember that data is one of the key elements of a machine learning model. So, thanks to statistics, we will be able to define in a rigorous way what is data, how can we handle it, and how we can define machine learning models on data, using data. In fact, in this course, we will study the foundation of probability theory and then apply those information in the construction of some statistical tool that can be used, for example, in a data science project. But first, let's recap what we have done since now. In the first course, the one about linear algebra, we studied vector spaces, the most simplest space where we can define some obvious operation and properties between its elements, the vectors. Then we have defined matrices, particular objects that are very useful when we want to do multiple operations, but these operations are very simple. Matrices allow us to use a simpler notation. Finally, we have talked about basis and how the basis, the concept of basis, thanks to linear mappings, represent the way how we view the vector space and how we can change perspective about it. In the second course, the one about analytic geometry, we have defined, in fact, some geometry concepts. Like if we want to define the length of a vector, we use norms. If we want to measure the distance between two vectors, we use metrics. Finally, metrics and norms are induced by a particular operation, the inner product. Thanks to the inner product, we are able to define and construct orthogonal projections. So we take a vector and we can project it in an orthogonal way in a subspace, thanks to again to the inner product definition. Finally, we have studied how rotation can be represented in a linear vector space. Third course, the one when we talked about determinant, which is a measure of the way a linear mapping changes the parallelepiped volume and how the vectors are stretched and rotated. The determinant inherits this concept through its definition, but is very useful when we want to introduce eigenvectors and eigenvalues. The eigenvalues make us understand linear transformation in an easy way. In fact, they represent the direction along which the linear transformation acts simply by stretching and compressing the vectors and/or flipping them. Eigenvalues are the factors in which this compression, for example, occurs. Then we have seen how eigenvectors and eigenvalues can be used to simplify a matrix. If we have a diagonal matrix, the easiest way to simplify it is to eigendecompose, which means to transform the generic matrix, diagonal matrix, squared matrix into a diagonal matrix. The eigendecomposition is not always possible, so in other cases we can use with square matrices the Cholesky decomposition, and for generic metrics, rectangular matrices, we can use the singular vector decomposition. Some machine learning models, in fact, are based on the singular vector decomposition theory. In the fourth course, we have talked about how things changes and how can we measure them. So we have introduced the concept of limit that allows us to analyze the behavior of a function when approaching a point, not in that point, but when approaching it. So this means that the point can be not in the domain, exactly in the domain of that function, and also in approaching that point we can measure in some sort the behavior of the function. So thanks to the notation of limit, we can identify some particular function, particularly regular, the continuous functions. With the limit, we can define the derivative and, in general, the differentiation, in which we compute the infinitesimal variation of a function with respect to a point. Also, an important note is that the direction of steepest ascent is the same direction as the gradient, or the derivative, if we are in a unidimensional function. Then, in calculus is based on the differential calculus and integration calculus. Now, let's talk about the integral calculus. And we've seen that there are two types of integrals, the indefinite integral and the definite integral. The indefinite integral comprises all the antiderivatives, the opposite operation of a derivative for any given function and at any point. So the indefinite integral is the antiderivative, all the antiderivative, because we've seen that we can take an antiderivative and then plus sum with something constant, and we get another valid antiderivative for the same function and the same point. Then the definite integral instead allows us to compute the signet area under the function between an interval. Those two concepts are linked together, are tied together through the fundamental theorem of integral calculus. So, moving on, let's talk about the statistics. And we will see this fourth section. We first look at some theory, the measure theory. Then we will leverage this theory to describe probability and distribution, and through them do some statistical inference and see how statistical inference can be used to develop some data science tools. Let's talk about, first of all, about measure theory. And we will see that the probability can be seen as a measure of uncertainty. But let's deep dive on the concept of probability. In common parlance, we refer to probability when we are unsure about a given event. And the uncertainty, we can say, that is due to an incomplete knowledge of the phenomenon, of which we prefer not to foresee a certain outcome with absolute certainty. Of course, we are linking together the concept of probability and uncertainty. So, leaving out, let's leave out quantum aspects and quantum mechanics. But in a macroscopic way, if we had total knowledge of the phenomenon, it would be absolutely not necessary to study it through the theory of probability, to the unknown, study of the unknown, because we have the full knowledge, the complete knowledge of the phenomenon. So we can study it study it in a sort using deterministic formulas. Now instead, in this course, we will talk about probability and statistics. So let's think about the wheel of fortune. If we knew the force with which we are making it spin, its mass, the friction with the pin and the air, etc., everything that physicists want to know, the outcome will be very far from uncertain. Of course, we will get one number. We will get the one slice where the wheel will stop. But we need a mathematical space. Since this is not possible, for example, we need a mathematical space where some intuitive properties regarding probability, so the uncertainty, are satisfied. This mathematical space should be a space that will allow us to measure the uncertainty on it. That's why we will talk about the measure theory, and we will first define the sigma algebra. Here we will always think about a generic set of elements, omega. And in omega, we define a collection of subsets of omega, such that these three properties are true. Then this subset is said to be a sigma algebra on omega. What are the three properties that define a collection of subsets of a set as a sigma algebra? Well, first of all, in the collection of subsets, the null space and the full entire space should stay inside the sigma algebra. Then, if we take a set inside the sigma algebra, then the complementary omega minus this set should also stay inside the sigma algebra. Then, if we take a collection of subsets uy, and each of them lie inside the sigma algebra, then also the union of those sets should also stay inside the sigma algebra. In the second property can be defined as the sigma algebra is closed under complementation. In fact, here we are taking the complementary of the set U. The third property can be expressed as the sigma algebra is closed under countable unions. In fact, if the elements of the union stay inside the sigma algebra, then also the union should stay on it. From the true properties of closure that we have seen so far, it follows also that the sigma algebra is closed under countable intersections. That's fine. So we have the property of the null space. Let's start from here. Then the null space and the entire space are inside the sigma algebra, the closure under complementation, and the closure under countable unions, and finally the closure under countable intersections. That seems a strong definition of a sigma algebra. In fact, if we pair together the first set of elements and a sigma algebra defined on this set of elements, we define a measurable space. And this is the first brick that we will use to define the measure theory and how probability can be described as a measure of the uncertainty. The elements of a sigma algebra are called measurable sets. Sets that can be measured. as maybe you have already seen, there's a link between the properties of the topological space that we have defined in the previous course, talking about calculus, and the measurable space. In fact, the first property is the same. Then we have in the measurable space that is closed under complements, under complementation, that is not required in the topological space. And then we have similar closures under countable unions and under intersections, but in the topological space we have arbitrary unions and finite intersections, and here we have countable unions and countable intersections. So there should be some intersection here between topological space and the measurable space, given of course a set of elements. And we want to discover what is this intersection, because thanks to this intersection we will be able to develop the probability theory thanks to the measure theory, and also we can use the concepts we have defined in the previous course, so limits, derivatives, integrals, and so on, that we have defined in this blue space. And now in this orange space we will define probability. It would be nice if we can do both in here, in this intersection. And to do this, we will start by taking the generic set of elements, omega, and we will define multiple sigma algebras on omega. It's the same as in the topological space. We can define multiple sigma algebra on a generic set of elements. So if we take the intersection of an arbitrary family of sigma algebras, we get another sigma algebra. That's fair. That could be used in the further slides. So remember, if we take intersections of sigma algebras, we still get a sigma algebra on omega. So now, given the generic set of elements omega and any collection of sets F, so in F we have a lot of subsets of omega, we can always define a particular sigma algebra that will be indicated as B of F, which is the sigma algebra generated by F, the collection of sets of omega. And how we can define this sigma algebra? Well, we take every possible sigma algebra that can be defined inside F, and then we take the intersection between them. As you can see here, since this F is already a collection of elements, we just have to take the subsets that make F alpha as a sigma algebra. Then we take all the possible F alpha and we do the intersection between them. Since the intersection of sigma algebras return to us a sigma algebra, then B of F is still a sigma algebra and is generated by F. Also, the intersection of all these sigma algebras results in the smallest sigma algebra containing F, since we are taking the intersection, not the union, of course. And remember that here I pointed out that we can take any collection of sets F. So it could be also a topology. A topology is a collection of sets on a generic set of elements. In fact, if we take a topological space where tau now becomes our F, So the collection of elements now is a topology. The sigma algebra generated by tau is called Borel sigma algebra, and the elements of the Borel sigma algebra are called Borel sets. The definition is the same, we just replaced f with tau. For example, let's see what a Borel sigma algebra is on R, the real space. Well, we have seen that on R, the open intervals are open sets. And we can define a topology on the space thanks to the also open intervals. Well, on R, it can be shown via induction that every set of open intervals or closed intervals or left open, left closed, left open or right open intervals are all Borel sigma algebras on the real space. Usually, mathematicians use open intervals, so there's almost no distinction between topology and Borel sigma algebra on the real space. If we use, if we define the Borel sigma algebra as a set of open intervals. Moving on, we have seen that a set of elements plus a sigma algebra give us a measurable space. What we can do in this space? Well, if we take two of them, two measurable spaces, we can define a function that goes from the set of elements omega to the set of to the set of elements omega to the set of elements of theta. And this function, since on omega we have defined this x as a sigma algebra, and on theta we have defined y as a sigma algebra, is said to be xy measurable. So a function that can be measured thanks to these two sigma algebras. If we get this property, we will usually refer to this property of the sets where f is on V. This means that we are getting all the elements of omega in which, taking the f values, those results stay in V. And these omegas that in which this expression results true stay inside the sigma algebra defined on omega, and this is true whatever V is. This is the property that defines a function measurable, a measurable function. So if we look at the y's, we could say we are able to come back and still stay in a sigma algebra. Of course, the sigma algebra in omega. Of course, we can take a particular sigma algebras, the Borel sigma algebras. Then omega x and theta y would be Borel spaces. Then f will be simply called Borel function. Again, there should be some link between the measurable functions and the topological and the definition of continuity inside the topological spaces. In fact, you can see that the two definitions are very similar. Given, let's look at two spaces Rm and Rn, and we defined two topological spaces here. And on the same set of elements, on the same real spaces, we define also two Borel spaces, two Borel sigma algebras. So for the same Rm and Rn, we have topological space and a Borel space. We can say that if the function that goes from Rm to Rn is continuous, with respect to tau and sigma, of course, then this function is also xy measurable. So the continuity means that the function is also measurable. That's a useful property, and it's very important because it remarks again the link between what we are doing now with the measurable functions, with the measure theory in general, and what we have done in the previous course. Here is the proof. So the sigma algebra is generated here, as I previously mentioned, could be generated by the set of elements of all open sets. So the sigma algebra is a collection of all open sets. Since the function is continuous, then it maps open sets to open sets. That's the property of continuity here, defined on the topological space. Then also we get that the function should map also elements in the Borel sigma algebra to open sets. There are again elements of the respective Borel sigma algebra. Now we have talked so far we have talked about measurable space, a space that can be measured. Now let's see how we can measure that space. And so let's start with omega A, a measurable space, and we define a particular function mu that goes from the sigma algebra to a positive value. And this function is said to be a measure on A if it satisfies three properties. Let's start from left. The non-negativity property. This means, of course, that whatever is the set of A, the measure of A should be greater or equal than 0. That's the definition, in the definition. There's another property on the right, the null empty set property, which means that if we measure with the function mu the element, the null space, then its measure is equal to 0. So again, it's like a ruler in which we have to define the start of the ruler, and then we can define some sort of unit to measure. But we have also to always to define where to start to measure. So we start from the null element, which has measure 0, and then we say that all the other sets will have a measure equal or greater than 0. Could be also plus infinity. That's nothing wrong with that. It's in the definition of U. Here we are taking the plus infinity as a possible value of a measure. And then we have another property called the sigma additivity. Here let's take a set of a collection of sets that are pairwise disjoint, which means if we take the intersection between uy and uj, it will give us the null set. If we take the measure, excuse me, here there's an error. a union is intended here. We take the union of all the sets that are inside of this collection, and we measure it. We get that is the sum of the measure of the single set. It's an additivity property that we are doing using elements sets in a sigma algebra. So taking the measurable space and adding a measure on it, we are defining a measure space. Finally, we are in the core of the measure theory, of course. And particularly, since the three properties that define the measure, we can say that mu is monotone. In particular, a measure has the property of being monotone in the sense that if A, for example, this inner set, is a subset of B, this bigger one, the measure of A will be less or equal than the measure of B. Here we go. That's our ruler, and that's our sets that we want to measure. So, since this is bigger and this small one is a subset of the bigger one, the measure of the smaller is less or equal than the measure on the bigger one. Let's see an example of measure, the counting measure. For example, let's say that the simplest one is if A is finite. So we can count the elements of the set. For example, we have a basket of fruit, apples, oranges, and bananas. Then we can count all elements. So the counting measure will give us the number of elements in this particular subset. Let's say that the entire basket is our omega, then A will be a small set, a subset of omega, and we count the elements of this subset. But we can define more constraints on the measure. In particular, for example, we can say that we can impose that the measure of the biggest computed on the biggest set, the omega set, the entire set, should be a number less than infinity. So we are putting a constraint on the measure, and we are saying that the measure should be finite. If we say that the measure of omega should be equal to 1, then this is called probability measure, and will be in the next section denoted as P. We will forget about the mu notation and we will use P. Also, omega, A, the sigma algebra defined on omega, and P, the probability measured on A, will be called probability space. But let's don't spoiler too much. We will see this in the next section. What we want to cover now in this section is the Delabek integral. And to do so, we will define another special measure on the real space, and that's the Delabek measure. So let's take an n-dimensional rectangle. Here we have an open interval for every dimension. We have a box, a sort of box, and we define the volume of this box as 0 if the box is the null set, alright. But in normal condition, that's the Here we have the length of the, and we multiply each dimension, the length for each dimension. That's our volume. Seems fair since now. How can we get to the Delabek measure? Well, we have to define another particular concept, the concept of covering. And we can say that a covering of a set B that stays in Rn is a countable collection of open rectangles such that B is a subset of the union of these sets. So what we are doing here, A are rectangles, and B, let's look at it in 2 dimensions. Let's say B is a disk on the 2D space. Covering the B set means that we take small rectangles, for example, let's say squares, that are particular types of rectangles. We take small squares and we try to cover with a lot of squares the disk, such that the disk will be inside all the union of our collection of squares. So we can use how many squares we want. What we can do? Well, the Delabek's measure is defined such that the volume of is the infimum of the volume of this collection of rectangles, such that A is covering B by open rectangles. The second line expresses it in a more explicit way. So what we are doing here, we are covering the space, for example the disk. We are talking so far. We are covering the disk by open intervals or open rectangles. Alright. We compute the volume, but we want to compute the volume of the infimum. So we have to take in account the set that the collection such that the volume will be at minimum. But this collection of open rectangles should also cover entirely B. So we are covering, but we want the minimum measure, the minimum volume. That's the Delabek measure. And this picture in the book, in the cover of this book, is extremely clear about the concept of Delabek measure. As you can see here, we have a collection of open rectangles that are covering B, our dotted line space. And what we are doing here, we are taking the measure of B such that we get all those rectangles here are squares, but doesn't matter. We take all those rectangles and we take the minimum. But also here we have these rectangles are not, the squares are not enough because they do not cover completely the space. So we have to start from more rectangles and get smaller and smaller, since we are very close at the limit, and we are doing here implicitly a limit to the real volume of B. Of course, in more technical details, in order to use the Delabek measure, we will need to complete the Borel sigma algebra, but we will not talk about it. I think that this is enough to understand how the Delabek measure is, how it works, and thanks to this definition, we will be able to use it in the next section. So we have defined the Delabek measure. How can we get to the Delabek definite integral? Of course, we will use the Delabek measure, but we will use it step by step, increasing the difficulty of the definition of the Delabek definite integral. So, for example, we will start from a simple function, that's their name, to go to the most generic type of functions. We will see that the simple functions are finite real linear combinations of indicator functions. But first, let's start with indicator functions. What are the indicator functions? Are this type of functions. One, and here we get the set in which we are using the indicator function. This means that this function is equal to 1 when we compute this function with an element inside the set S. Outside the set S, this function takes value 0. So this is our first definition of Delabek integral. We will write the measure under this D by convention, and the integral of the indicator function is the Delabek measure of that set. Now let's define the simple function. It's a linear combination of indicator functions, as you can see here. Lambda k is a coefficient that is applied to the indicator function. So this term, this lambda times 1 times the indicator function, means that we get a function that has the same behavior of the indicator function, but instead of getting me 1 inside the set S, k, it will give me lambda k. Here we are taking the sum, and we want to compute. What we do, we express here the linearity of the integral by defining it in this way. So is the linear combination of the lambda times the Delabek measure on the SK set. Here you can see the concept of a simple function. For example, here let's say that this level is 1, and this level is about the double, is the double height of the smallest step. This means that the lambda k here is equal to 2, and this column here is one element of this combination, linear combination. We have defined simple functions. Now let's define it. Let's increase the complexity of the function, and let's do it with the non-negative functions. So f here is non-negative, so could take values equal or greater than 0 in its domain. How we define the integral? Well, we will take all the simple functions S, we will call S, the simple functions, such that the value that simple function takes are between 0 and f. So f, for example, in this 2D graph, should stay beyond the f line that is in here in black. We compute the integral of the simple function, and then we say we want the supremum of this integral on the simple function. This implicitly means that we want to find the simple function that is closer to f. Again, we are doing a sort of limit here. Finally, we will define the Delabek integral for a sign function. Here, a sign function could be written as a positive part and the negative, in which the positive is equal to f of x if in this particular x we get that f of x is greater than 0, and then f plus is 0 otherwise. The same, but with a minus in the f minus definition. So f plus and f minus are both non-negative functions. In fact, here we are doing f plus minus f minus. So f plus and f minus are non-negative measurable functions. We can say that the Delabek integral is defined. We are just saying that is defined if at least the integral on f plus or the integral of f minus are finite. It just matters that one of the two are finite to say that the Delabek integral is defined. But we don't want only to define the Delabek integral. We also want to compute it. So if the Delabek integral is defined, then we can say that for a sign function, the integral of the sign function is equal to the integral of this non-negative function minus the integral of this non-negative function. We will say that f is Delabek integrable if both are finite, both the integrals are finite. So this means that we get here a real number, and not a plus infinity or minus infinity as a value for the Delabek integral. With this in mind, we can finally compare the Riemann integral and the Delabek integral. Here we have, in the Riemann integral, remember that we have used two sorts of histograms, and we have in some way took the limit such that the supremum and the infimum were the same. In this Delabek integral, instead, we are using some sort of horizontal histograms, using the indicator function and the simple functions. But the Delabek integral are more powerful than the Riemann's one. And to show you, let's take an indicator function that is defined with s equal to the set of all rational numbers, the fractions. Looking at the Riemann integral, we can say that the indicator function on Q is not a Riemann integrable. For example, let's use 0, 1, the interval 0, 1 for simplicity. Why? Because you can choose whatever partition you want, but inside each subinterval you will always find at least one rational and one irrational. The real numbers are dense. Give me two numbers and I will always find one rational, one fraction inside the two numbers that you gave me, and one irrational number. So the lower Riemann sum will be always equal to 0, because when the indicator function on Q will be computed on an irrational number, it will give us 0. But the upper Riemann sum will be equal to 1. So the lower Riemann sum and the upper Riemann sum are not equal. So the Riemann integral could not be computed here. Instead, with the Delabek integral, we can say that all one-point sets are null, will have measure 0, and therefore all countable sets are null. Well, we can take 1 point at a time, and we can say that each 1 point set has measure 0. So one of the countable sets here is the set of all rational numbers. So the rational numbers are a null set. And so this means that the integral of this function is equal to 0. This can be seen, it can be expressed in another way as a null Lebesgue measure. They are an important concept in measure theory, the null Lebesgue, the null sets. And a null set is a set in which, let's take the subset n of R, and this n has null Lebesgue measure, so it's a null set, if and only if it respects this formula. So let's take whatever epsilon, positive epsilon, and let's take a set of intervals, and we have that n is covered by this set of intervals, but the measure of this set of intervals, that the union of this collection of intervals, is less than epsilon. For example, looking back to here, yes, I said to you that the 1 point sets are null sets, have measure 0. Why? Because I can always find you a collection of intervals. Give me one epsilon. It could be greater or smaller, how you want, but I always find a collection of intervals such as they always cover. They will cover the point, so the point is inside the interval, but also I will find those intervals such that the Lebesgue measure on the union of these sets will be less than epsilon, the epsilon you gave to me. So that's the conclusion of the measure theory, and we've seen how the sigma algebra and the measurable space, we define a measure, and the measurable space plus the measure give us the measure space, a space where we can measure things. Now we have defined a particular measure, which is the Lebesgue measure, and thanks to it we can use the Lebesgue integrals. Now we want to use the measure space, and as I mentioned previously, we want to leverage it to define probability and define distributions.